All right, so this is where we left off in Lecture 8, talking about light as it was understood in classical physics, by analogy to an ocean wave. A young German guy named Max Planck, not Planck, Planck, at the end of the 19th century there, decided to try and solve the problem of blackbody radiation. Now, a mathematical proof, the way that works, is that, you set it up like this. Here are your assumptions, and here's your steps 1, 2, 3, 4, 5, and so on, and that leads you down here to your conclusions. Okay. Now, if your assumptions are true and your work is good, then your conclusion will be true. Okay. Now, as we saw from the ultraviolet catastrophe, their conclusion was wrong. So that meant either their assumptions were false or their work was bad. Okay. So what Planck did is he looked at the mathematical proofs, the work that physicists were doing to come up with this piece of garbage down here, and he saw that their work is good. Now, if good work leads to a false conclusion, then it must be the case that their assumptions were wrong. So, he decided to change some of the assumptions. This is perfectly fine in physics. A lot of physicists do this, and they publish papers. It's called theoretical physics. You just play around with your various assumptions. You say, okay, what if this was different? What if this was different? What if this? And then you just sort of build to different results. See what happens. You just play around with it. If you come up with something completely absurd, then you still publish, but you might not expect anyone to try and figure out whether you're wrong. If you come up with something interesting, then they'll try and figure out whether you're wrong. Now, so what Planck did was he treated light as a wave, but completely different from ocean waves. Okay? Whereas ocean waves are sort of a continuous spread of energy, he decided to treat light as being made up of individual packets of energy. Individual units. Okay? Unit comes to us from Latin, means one, a thingy. So he came up with a thing from also Latin. He came up with quantum. Quant means count, so a countum, a thingy. Okay? So that's where quantum mechanics comes from, because it's just single bits, single particles of energy. Okay? So he took that and he did a lot of god-awful math, and he got the right answer. I'm not going to show you the math, I'm just going to show you the result. Okay. Up top here, this smaller answer is the answer that classical physics came up with, and it's the wrong answer. As you can see, it goes as a function of nu squared. That's the square of the frequency. So as frequency gets higher, as wavelength gets shorter, that line just keeps going higher and higher. That's why they got the ultraviolet catastrophe. Now, you'll see that Planck's answer, it contains their answer. It's obviously related, but it has a whole lot of extra stuff over here. Okay, and the real extra stuff comes from this term right here, h nu. Okay. H nu. Okay, so nu, as we recall, is just the frequency of the light. H is what is now known as Planck's constant. Okay. Very often, when you are doing math, you end up with new constants coming into your equations, whether you want them to or not, usually when you do integrals. So, like, the integral of x is 1/2 x squared plus c. Just some random constant. You don't know what it is. And h is the the constant that showed up in Planck's work. And he realized that it had an actual sort of physical meaning. H equals 6.626 times 10 to the negative 34th joules per second. Okay, it's just something that's there to balance the energy of the light against the frequency of light, okay, so that you can get that intensity measure. Okay. So energy versus frequency, basically, is what we're looking at with that plot. Or against wavelength, and then you just flip the graph around is all. All right. So it was an entirely different way of looking at light, and you would expect that he came up with the right answer, as you can see there, and you would expect that physicists would fall all over themselves saying, wow, he must be a genius who is absolutely right. Well, not so much. Planck said it might not actually be real. It might just be a formalism, sort of like the electric field, just a way to deal with it mathematically that gets you a useful answer. Everyone else said, shut up. They got all pissy. What Planck actually said is here in the German, if you can read German. I can't, so I'm not even going to try. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. In other words, there in the late 19th, early 20th century, he came up with a principle of postmodernism. Science advances one funeral at a time. Very grim, very German. But yeah, that's kind of the way it is. Progress always happens, as people either are convinced or grow up and realize, just grow up with it and realize, oh, that's the way it always was. Okay, so Planck didn't necessarily think it was a physical reality. Maybe he thought maybe it was just sort of a way to play around with the math. But somebody else came along to look at another physical phenomenon. In this case, the photoelectric effect, and he applied Planck's new quantized view of light. Now, the photoelectric effect is if you shine light, light in Greek is photos, on a piece of metal, then you get an electron occasionally flies off. Okay, so photoelectric. And that's the photoelectric effect. All right. So this electron has some kinetic energy. Now, according to, again, the classical conception of light, if you increase the amplitude, the intensity of light, then your electron should come off with higher kinetic energy. And according to the classical conception, the frequency of light should make no difference whatsoever. Now, in reality, when you look at the electrons that are coming off of metal when you shine light on them, the higher frequency of light gives you electrons with more kinetic energy, and higher amplitude gives you more electrons. Physicists had no idea what to make of this, but a Swiss patent clerk with a little bit too much free time on his hands took a look at Planck's equation, repeated here on the right, and thought he saw the answer. He saw it in h nu. Okay? He saw that Planck got it exactly right, and that his formula was not just, a handy fiction. Because h nu, h has units of joules. Oh, no, sorry, not joules per second. Oh, dear, if you're taking notes, you're going to have to change it. It has units of joule seconds, and frequency has a unit of per second. So h nu equals joules. H nu gives us energy. Okay, so what he realized, the energy of an individual photon of light is equal to h nu. Okay, a photon, from again Greek photos, just means a particle of light. So as the frequency of light increases, the energy increases, and vice versa. All right. So what is happening as you increase the intensity of light? Okay. As you increase the intensity, you are kind of increasing the energy because you're increasing the number of individual photons. So more photons, each one carrying energy. More photons means more energy. Okay? But higher frequency means each electron carries more energy. So intensity tells us about the total number of photons and the total energy carried by them. Frequency tells us about the energy of each individual photon. Okay? So this is the solution that Einstein came up with, okay? That h nu equals E. And he said, all right, so the kinetic energy of the photon, K max, is equal to h, well, he called it F, okay, h times the frequency, minus phi. That's the Greek letter, you often use Greek letters just to be fancy. And phi is what he called the work function, the amount of energy needed to remove an electron from the metal that the light is striking. Okay. So if you have, okay, here is your metal, here is your electron bound to the metal with an energy phi. It's the energy to remove your electron. Here you have a photon of light coming in with energy h nu, related to the frequency of the light. Okay. Okay. So when the electron pops off, the energy of that electron, the kinetic energy, is just the energy of the photon minus the energy tying it to the metal. Okay. So that's where Einstein came up with that formula. Okay. Yeah, clever guy. So if you look at this formula, what you see is that this doesn't change. Okay, the work function, the energy tying the electron to the metal, doesn't change. So as you change the frequency of light, you're going to have some threshold frequency. And below this, you'll have no electrons coming off the metal, and that's what they saw. Above this, you get electrons, and they get more and more kinetic energy as you increase the frequency. And that matches exactly with what you're seeing with the photoelectric effect. And that is actually what Einstein won the Nobel Prize for, not relativity. Photoelectric effect and his explanation is easily confirmed, and it rather radically alters physics. Relativity is confusing and difficult to confirm. In fact, you may have heard that back in this past year, 2016, one part of relativity was only confirmed this last year, gravitational waves predicted by relativity. So relativity was difficult to work with, but the photoelectric effect easy to work with. So that's what he won the Nobel Prize for. Nevertheless, it inaugurated the quantum era, the era of quantum mechanics, moved us into a new era of physics. And it also allowed us to understand the atom. We're moving past Rutherford's model with its orbits that remain completely unexplained. Okay. So a photon, like I said, it's from Greek. Phos means light. It's just an individual particle of light. And the thing that varies, a photon does not actually move up and down in space like this. That's referring to the electric and magnetic fields of that photon. You see, an electric field that's changing automatically causes a magnetic field to pop up at 90 degrees. So a photon is a self-contained little burst of energy that it's an electric field that varies, call it straight up and down. And then you have a magnetic field that varies left and right as the photon moves forward. So it's sort of a twist in the fabric of space, just bing, moving along from the place where it's emitted to the place where it's eventually absorbed. Okay. So, next time we are going to look at hydrogen, or possibly helium. Give me a second to recall. And we'll move on from Einstein.